The title of this lecture, You Can't Trust Everything You Read. As Trump says, there's a lot of fake news out there. And when it comes to medical research, that actually is true. That actually is true. That a lot of what you read is inaccurate. So the place I got the idea for this lecture was from a paper. It's the most downloaded paper of all time from the Public Library of Science journal. And the author is John Ioannidis. I hope I said his name right, but he's a professor from Stanford. And if you're interested in research or scholarly activity, you should read it. So I'm going to tell you a couple of the key concepts from this paper and then add in a couple key concepts of my own. So this is a quote to start you off. Simulations show that for most study designs and settings, it is more likely for a research claim to be false than true. Moreover, for many scientific fields, claimed research findings may often be simply accurate measures of the prevailing bias. So John Ioannidis is simply stating here that medical publications are often fake news. The question is, why is that the case? So there are a bunch of reasons, but I'm going to give you 3 big reasons. The first reason is based on how we have defined statistical significance. So as many of you know, we define a result as statistically significant if you get a p-value less than 0.05. Well, guess what? That gives you a 95% confidence interval. You're 95% confidence that you're right, which means that 5% of the time you are guaranteed to be wrong. All right? So knowing that you are 5% of the time going to be wrong, it means that even if everything else is done correct in a study, the methods are perfect and there's no other bias, still 5% of the studies are wrong. So there's your 5% baseline must be wrong. Now, this spirals out of control. So let me explain. As an example of a hypothetical study. All right, so some local Miami person on a blog says that they think that drinking cafecito improves neurologic outcomes in acute stroke. All right, so 20 researchers throughout the world see this blog post and they're like, it sounds kind of stupid, but maybe it really works. So 20 different groups decide to test if cafecito helps with acute stroke. So they randomize patients and they give them either cafecito or placebo coffee, whatever that is. All right, they assess their neurologic outcomes at 6 months, and 19 of those 20 groups correctly conclude that actually cafecito does nothing for acute stroke. But just by chance, one of those 20 groups finds a statistically significant result, because I just told you 5% of the time that's what happens, all right? Just by chance, the groups were unequal, and for whatever reason, it looks like cafecito actually helps for acute stroke. All 20 of those people then submit their results for publication. But the 19, when they submit them to journals, the journals are like, this is the stupidest thing I've ever seen. Of course cafecito doesn't help with stroke, so all their articles get rejected. But the one person who finds the statistically significant result, the journal that reads that is like, this is the most amazing thing I've ever read. Cafecito helps with acute stroke. Who would have thought that, right? So even though the studies had been negative 19 out of 20 times, 1 out of 20 was enough, and that one got published. That is called publication bias, right? So even though a small percentage of the time you find the incorrect result is more likely to get published than the correct result. That is publication bias. As a result of publication bias, it is essential that studies be replicated. So if you see a study that seems too good to be true, or where it doesn't make a lot of scientific sense, like if someone told you that cafecito helped with acute stroke, you should not apply that to your practice until that result has been replicated. Example of that recently, I don't know if you guys heard about the vitamin C thiamine cocktail in sepsis. For all I know, that works. It might. But only one study has ever been done. It had poor methods, and its results are way too good to be true. So based upon evidence-based medicine principles, you should not be applying that study to your practice yet. All right? If somebody else does that study in a randomized controlled method and finds the same result, all right, I'll be on board. But I'd be willing to bet that there's a high chance that that result is not as good as what that first study showed. I doubt that vitamin C is really a life savior in sepsis. All right? A second corollary to this issue with the p-values is that if you measure a whole bunch of outcomes in one study, you are even more likely to find something incorrect. So you should focus your attention on the primary outcome of the study. Study's statistical power is designed to look at the primary outcome. But if a study looks at one thing primarily and then also looks at 20 secondary outcomes, one of those 20 secondary outcomes likely is going to falsely be statistically significant. Just because if you look at enough stuff by chance alone, you'll find something statistically significant. So be very careful if something is a secondary outcome. Be careful about applying that to your practice. All right. Problem number 2 out of the 3 I'm going to discuss. Conflicts of interest are rampant. When I say conflicts of interest, I can mean financial or academic. Even our faculty has some publication pressure. We must get some certain number of PubMed IDs, but we're not super malignant about it. But if you were to go to a big Northeast academic institution where there's even more pressure, you may get fired if you don't get enough publications. There is a lot of pressure on you to generate interesting data that can get published. And as a result of that, even if you're trying to be ethical, it is likely that your subconscious bias is going to result in you presenting or finding data that's not correct. Financial bias, of course, is rampant in the pharmaceutical industry, publishes a large percentage of studies. We'll talk about that again on the next slide. But even if you have all of the best intentions, again, you're going to sometimes find the wrong result by subconscious bias. On the other hand, sometimes people simply lie. And this has been studied, and a study from the Public Library of Science in 2009 took a survey of a whole bunch of research physicians, and they said that about 14% of them said that they specifically knew of an instance where a research data had been fabricated. All right, so 14%, I would guess that it's at least that high. And there's just too much pressure on people to generate data for their own careers or to make money. So people lie. That's the crux of it. New England Journal of Medicine still has the highest impact factor. In 2008, it actually had by far the highest impact factor, and some consider it the best journal in the world for medicine. But even they are subject to massive amounts of bias. So this is not from a research article, but from a newspaper article where they reviewed New England Journal of Medicine's publications over a 1-year period and found that 80% of those studies that they published were funded by a pharmaceutical company. When the highest level of evidence that we have in the most respected journal is that biased, we have a huge problem in medicine. And we are basically being run by pharmaceutical companies. Here's an example of how this goes wrong. People heard of the story about Vioxx before? A couple people. All right. A couple people. So Vioxx, also called rofecoxib, something like that. Rofecoxib was a selective COX-2 inhibitor. As a background, most NSAIDs inhibit both COX-1 and COX-2. But COX-1 is involved in protection of your GI system. And so the idea was by making a selective COX-2 inhibitor not inhibiting COX-1, you could avoid some of the GI side effects in an NSAID. And so that was the idea behind selective COX-2 inhibitors and rofecoxib. It was FDA approved in 1999, and a big study came out in New England Journal of Medicine in 2000 looking at the toxicity of naproxen versus Vioxx, okay? And in that study, they found just a slight increase in the rate of myocardial infarction for the patients in the Vioxx group compared to the naproxen group, but the difference was so small that people didn't think it was really that big a deal. And there was definitely a decrease in the number of GI adverse effects in the Vioxx group compared to the naproxen, so overall they said, hey, this probably seems like a good thing. However, it was later discovered that somebody, let's say maybe intentional, but let's be honest, it was intentional, erased 3 patients who had a myocardial infarction from the data set. Without those 3 patients with myocardial infarction in the data set, the increase in myocardial infarctions looked really small, but once you added 3 extra patients who had MIs to the Vioxx group, it became very clear that this drug causes myocardial infarctions compared to naproxen, which is not good. Later, a study in Lancet estimated 88,000 Americans had MIs as a result of taking this medicine. And 30,000 plus of them died from a myocardial infarction, simply because some researcher lied about their data. The last problem associated with research that I'm going to discuss has to do with methodological and statistical errors. So the point of Journal Club, or at least one of the points of Journal Club, is for you guys to learn how to assess for methodological errors in research studies. That's what we mainly focus on. And also, so methodological errors are much easier to teach than statistical errors. And we don't focus much time on teaching you statistical stuff. And part of that's, of course, my fault. I intentionally don't focus a lot of time. But I really just think that if I gave you a lecture on statistics, nobody would learn anything anyway. The way that you learn statistics is really by actually trying to do statistics. And as a side note, if you want to learn how to do the statistics, you can. But the point here is that in addition to methodological errors, statistical errors, which shouldn't really happen very often, are very common, even in high-end journals. So somebody once said this: how can you make the correct conclusions from your data if you don't understand the statistics? If you guys have no statistical knowledge, how can you actually understand what you're reading if you read a scientific? A very good point. Anyone know who said this? Yeah, it's not someone famous. It was my sister. So she told me that about 5 years ago, because she's a statistician and a professor at Cornell. And I was like, yes, you are correct. And so since then, I have spent a lot of time learning much more about statistics. And she was totally right, that my understanding of what's going on in the literature is completely different now from when she said this before. All right. So is there evidence that there are lots of statistical errors? Yeah, there is. So there was a study in 2009. It's some statisticians looked at 55 submitted medical manuscripts, and 87% had at least one statistical error. So physicians, it turns out, aren't very good at statistics. Even when they have a statistician working with them, the problem is there's a disconnect between the statistician's knowledge of medicine, and so they can make errors because they don't understand the medicine. And so what you really need are researchers who understand the statistics and the medicine. Example of statistical nonsense. This is the IST3 trial. This is one of the big TPA trials. This study was specifically looking to see if we could extend the TPA window to 6 hours. As you guys know, I think, the TPA window is 4.5 hours, right? 4.5 hours from last known normal. This study wanted to extend it to 6 hours, and thank God we are not doing it at 6 hours. But that was the goal of this study. And they actually had a negative outcome. So there was not a improvement in neurologic outcomes when extending the window to 6 hours and giving TPA up to 6 hours. You did not get better neurologic outcomes at 6 months. But the authors write this: despite that, there's no difference in neurologic outcomes. They did a secondary ordinal analysis, provided evidence of a favorable shift in the neurologic scores at 6 months with treatment. And they show this. If anybody can explain to me what this means, I will buy you 100 beers. All right? I looked at this for like 10 minutes trying to figure out how this showed some statistical difference between the TPA group and the control group. And I believe they did some statistical test that showed some difference. But I know a lot about statistics, and I have no idea what they're talking about here. All right? So if I can't understand what they're talking about, that means 99.9% of people who are reading this paper don't know what they're talking about here. And yet people will read this and be like, hey, look what these guys found. And they'll act like this was a positive outcome. All right? So this is statistical wizardry, an attempt to show that a drug that totally failed its primary outcome still had a benefit. And so some people who are supporters of TPA will use this is their evidence right here, this graph and this statement, that IST3 actually was a positive trial, it was clearly a negative trial. All right. So if you are concerned about the future of research, I am too. But I do think that there's hope. The hope is that you guys are going to learn how to do this differently. You guys are going to be less biased. And you guys are going to learn how to interpret the literature with skepticism. And if you have studs like these guys, smart guys leading the way, then hopefully things will be better for the next generation of medical research and medicine in general. That's it.